The concept of dimension rests on one fact. Two different bases for the same space always contain the same number of elements. That common number is called the dimension of the space. It tells all there is to know about the space to within isomorphism. An isomorphism between two spaces exists exactly when they have the same dimension. The book considers only finite dimensions. Otherwise, the dimension is an infinite cardinal number. A lemma first. If the space is finite-dimensional and a map from it to itself is surjective, it is an isomorphism. Take the smallest number of elements that can span the space. That set is a basis, and since the map is onto, the images span too and are a basis as well. The theorem, all bases for a finite-dimensional space have the same number of elements. The proof is by contradiction. Suppose one basis is smaller, and split the larger coordinate space in two so as to build a projection onto the smaller piece. That projection can then be written as a composition of two isomorphisms, so it is an isomorphism itself. But it carries the last standard basis vector to 0, which is a contradiction. So no basis can be smaller than another. The integer common to every basis is the dimension of the space. The standard basis for coordinate in space has n elements. So coordinate in space is n-dimensional in this precise sense. A corollary, two finite-dimensional spaces are isomorphic exactly when they have the same dimension. One direction holds because an isomorphism carries a basis to a basis of the same size, the other because both are isomorphic to the same coordinate space. The theorem, every subspace of a finite-dimensional space is itself finite-dimensional. Each finite independent subset of it extends to a basis for the whole space, so their sizes are bounded. Take one of maximum size, and its span is the whole subspace. A corollary, every subspace of a finite-dimensional space has a complement. Extend a basis for the subspace to a basis for the whole space, and the linear span of the added vectors is a complement. Then two-dimensional identities. The first, the dimension of a direct sum, is the sum of the dimensions. The second is more interesting. The dimension of the sum of two subspaces plus the dimension of their intersection equals the sum of the two dimensions. Two more. The dimension of the null space plus that of the range equals the dimension of the domain. So when the codomain has the same dimension as the domain, injectivity, surjectivity, and bijectivity are equivalent. Last, the space of all linear maps has dimension the product.